All right, just to, I am going to come back to this, but I'm going to go to the lab stuff first because I want to make sure that we get through that and get that kind of off the table so that people can start turning that in and all of that. All right, so just a couple of things to remind you. Remember, if you were not here the day of the lab, I posted in Gizmo, posted in Classroom the assignment. You're going to use a Gizmo to complete. You're going to do that. So that was if you were not here the day that we conducted the lab. This is going to replace your lab report grade. All right. There is a quiz on the Gizmo. You need to make sure you do that as well because that'll replace your pre-lab questions. When you do it, you need to log into Gizmo through Clever and all if you have to. Other side, those that were here on the day of the lab, we're going to go through a few of the problems, making sure everything is being set up correctly. So looking at your lab report, these are kind of like the breakdown of the questions. So I'm going to kind of give some sample data that maybe that we would have had. So let's just say that I had 30 grams of water in the calorimeter. I weighed out a 50-gram sample, and do realize both of those actually go to 3 decimal places because my scales go to 3 decimal places. All right. So the temperature of the metal after heating before the calorimeter. So I got my metal up to 100 degrees Celsius. The initial temperature of the water in the calorimeter, it was 22 degrees Celsius after I had let it sit for just a few minutes in that styrofoam cup and all of that. And then the highest temperature attained after the metal is added to the calorimeter, the highest temperature I got was 34 degrees Celsius. All right. So I'm just going to show the math and all for one trial. I'm not going to show both and all that because it's the same calculation for each one. All right. So for question number 1, it says calculate the delta T of the water for trials 1 and 2. So remember that delta T is TF minus TI. So my TF for the water was, my final temperature for the water was 34 degrees Celsius because that's the highest temperature it got. My TI for the water was 22 degrees Celsius. All right, so getting that calculation, 34 minus 22 gives me a delta T of 12 degrees Celsius. Going through for number 2, this one was for the metal. Now, understand that the metal is going to give us a negative delta T because the temperatures are backwards. So TF for the metal is actually 34 degrees Celsius because that's what it ended up at. It's going to end up at the same temperature as the water in the calorimeter. All right. The TI for the metal is 100 degrees Celsius because that's what we raised it to before we did anything with it. So the same thing, I'm going to do, this case, 34 minus 100. That gives me a delta T of negative 66 degrees Celsius. All right. Now, getting to number 3. It says calculate the heat gained by water for both run 1 and run 2. So remember, when we're calculating heat, we're using Q equals MC delta T. Now, make sure you're using your numbers and not my numbers and all of that. So Q equals MC delta T. So we're solving for Q. That's what I want to know. My mass and it's saying water here. So the mass that I'm going to use for this one is 30 grams. For C, I have to look up the C of water. So I can use my periodic table reference sheet. I look up water, and I find that it's 4.184 joules per gram degree Celsius for a C. And then my delta T, we just solved for water, so the delta T for water is 12 degrees Celsius. So I plug it in. No, it shouldn't be. You're going to plug in whatever number you got right there, because that's for water. So delta T for water for me was 12. Whatever you got between your highest temperature water and your lowest temperature water. All right. So when I do this, I get a Q of 1,506. All right. And that's in joules. All right. Everybody's Q is, I mean, people within your group probably should get the same Q, but everybody's Q is going to be a little bit different because this number is different based on your group. All right. Everybody will have the same C. Also, your mass might be a little different based on your group. You may not have measured exactly 30 grams of water in there. All right. Things like that. All right. So for number 4, it says, what is the heat loss by the metal for both run 1 and run 2? What we have to understand. So it says, it makes a note here. It says, remember, energy is conserved. So understand that the amount of heat that was transferred from the metal to the water is the same amount of heat that was transferred within the metal. So the Q of water is equal to the negative Q of the metal. And the reason why I'm using a positive and a negative is because it says heat lost here, heat gained. So the heat gained is the opposite of the heat loss. So it's the opposite charge. So going there, now for number 5, it says using the information, calculate the specific heat. So we're going back to this equation, and instead of calculating for Q, I'm calculating for C this time. So I'm going to be using Q over M delta T. So this is my Q of water. This is my heat for water. All right. Because it's law of conservation, the heat that I gained in the water is equal to the negative heat that I lost in the metal. So I just get what I get there for the negative side? Yeah. All right. And so now I'm going to go ahead and plug everything in it, and it should make sense, and this is why we don't end up with a negative number for C. So my Q is negative 1,506 joules. My M, I'm going to look back at the mass of my metal, was 50 grams. Because we're looking at the metal now, not the water anymore. All right. And then my delta T is whatever I got for delta T for water. So I ended up with negative 66 for my delta T for water because that was my temperature change. So I'm going to put negative 66 degrees Celsius. And so when I do this calculation, I end up with a specific heat of 0.456 joules per gram degree Celsius. So now I can look at my specific heat table and all that and see if it matches up with something, but odds are it's probably not going to match up perfectly with anything on there, because this was a lab trial that we maybe didn't necessarily take all of the perfect care. We maybe missed the temperature a little bit, things like that. So this is a live example. In order to get one that's going to perfectly match something out there, we would probably have to do 20, 30 trials and get really, really good at this. All right, but we wouldn't have had time to do that. So now, the next question on there is asking us to use the calculation that it did in the pre-lab, where it says use the law of DeLong and Petit to average and the average value for specific heat to calculate the molar mass of the unknown metal. So my specific heat that I got, so the formula for that, I had to go back into that little packet that I used and all of that. But the formula that I got says molar mass times specific heat is approximately 6.2 calories per mole degree Celsius. So remember that the specific heat that I got right now was joules per gram degree Celsius. So the thing that I know that's not going to work right now is joules is not going to work. So I need to convert that to calories. And the way that I do that is, remember that 1 calorie is 4.184 joules. So when I do that, my new C that I'm going to use in this is 0.109 calories per gram degree Celsius. When I solved the previous question. Then you set something up incorrectly. Let me finish the overall thing. All right, so because I had 0.456 here, I can't use joules here. I have to use calories, so I had to convert that. That's why I'm saying that. So I'm trying to solve for molar mass. This is my C. All right, so degrees Celsius is going to cancel, calories is going to cancel. When I do 6.2 divided by 0.109, that's going to give me an approximate number equal to, I get 56.81 grams per mole. All right, or I could say AMU there. Now, what I'm going to talk about this, and again, this was a in-class lab sample. So I'm trying to figure out what metal I was working off of based off the information I have. So the two things that I can look at is I can look at my C that I got here on my table. When I look up my periodic reference table and all of that for specific heat, I find that iron's specific heat is relatively close. So I found out that iron had a specific heat of 0.449 joules per gram degree Celsius. I also found out that iron's molar mass is equal to 55.845. Now, these numbers are not exactly what I have, but they're relatively close, and when I compare anything else to it, nothing else really fits. All right, so I can say with a reasonable doubt that I believe that this was iron that I measured. For copper, you might have got a number close to 63 on your atomic mass, and you might have got a number close to 0.385 on your specific heat. All right. So again, you're not going to get perfect results on this. You'll never get perfect results unless you do it 2,000 times and average all those 2,000 trials. Then you'll get reasonably close because you'll get really good. Yes. The lab now. So I am not saying this is not the time to be working on your lab. You could take down what I showed you for notes, all of that. You can go back to this in the video. Let's switch over to the worksheet that I assigned yesterday. All right. This worksheet, front and back. Yesterday we covered ionic compounds, writing the formulas and naming ionic compounds. All right. So what we're expected to be able to do is to look at a formula and know what the name is, or look at the name and be able to determine a formula. So, based off of our rules that we got in the notes yesterday, where do I start naming this one? What's the first thing that I need to look at? I need to look at the first thing in it, which is Na. This is also what tells me that it's ionic, because sodium's a metal. Remember that ionic is always going to be a metal and a non-metal combined. All right. Now, realize that that non-metal here will sometimes just be an anion, like a polyatomic ion. All right. So I look up Na. I figure out that Na is sodium. Now, I have this other thing combined to it that is not just one element. So if I see that there's 3 or more elements in the compound, I know that this part has to be a polyatomic ion. How do I find out how or where do I go to find out the name of the polyatomic ion? Okay, I have to go back to my periodic table reference packet, look on the 3rd page of it, find the selected polyatomic ions and look it up. And so what do we find out is the name of CO3? Carbonate. All right, so sodium carbonate is the name of this one. Now, looking at number 3, number 3 is just a binary 1, so number 3 only has 2 different elements in it, so this one's a little easier. So again, I look up the name of the metal. Magnesium, right? Mg is magnesium. And then what about Br? What element is Br? Bromine. What do I need to do to the name bromine to make it work for a name? Change the INE to IDE, so I'm going to say magnesium bromide. All right. I don't worry about the number in the name. For ionic, I'm not worried about the number. Now, what's special about number 6? That's not what makes it special. What makes iron's a transition metal? So that means iron can have 2 different charges. So I don't know the charge automatically of iron, but I do know the charge of chlorine. What is the normal charge of chlorine? -1. So if I know that a compound has to have a 0 total charge, and I have 3 chlorines with a -1 charge, I can solve for my charge of iron this time. And I have to do that because it's a transition metal. So what is the charge of iron in this case? It's +3. So when I name this, I'm going to call this iron 3 chloride. Now, for this one, again, I have to distinguish this compound from this compound, so I'm going to do the same setup where it's equal to 0. I have 2 times -1, and this time my iron is not a +3, it's a +2. So that one's iron 2. All right. All right. So let's look at a couple of these. What's the symbol for sodium? What charge is sodium normally make? +1. It's in group 1A, it makes a +1. What, so if I change this back from phosphide, it's phosphorus. All right, so phosphorus is P. What charge will phosphorus normally make? -3. All right, so now when I react these two, doing my little crisscross, I'm going to say that it's going to take 3 sodiums for every 1 phosphorus, because all I do is flip it around. So it's Na3P on that one. All right. Let's look at number 23. All right. It says lead to sulfite. So I know that lead is Pb. What does that Roman numeral 2 right there tell me? I'm seeing lips move, but I'm not hearing anything. So it means it's a +2 charge. Thank you. All right. Now, we haven't seen an ITE ending yet on here. What should that ITE ending indicate for us? What ATE, ITE, what does that, should that automatically lead us to? Polyatomic. So I'm going to look at my polyatomic list. What is the compound, or what is the formula for sulfite? Sulfite is SO3? All right. SO3, sorry. I was just making sure. SO3 with a -2 charge. All right. So I see something here that you may not recognize yet. When I notice that both of these charges are the same charge, I know it's going to be a 1-to-1 ratio. So I can just put PbSO3 this time. Why don't I need parentheses around the SO3 this time? Yeah, because it's 1-to-1 ratio. This ion and this ion react in 1-to-1. All right. But if I look at, say, calcium phosphate, I look up calcium, calcium's a +2. I look up phosphate, phosphate is PO4 -3. So when I do this one, I have Ca3, PO4 2. All right. But because I need 2 phosphates, I have to put that 2 on the outside of a parentheses. All right. Now, I'm going to tell you, you probably got hung up on both of those because they don't fit any of the patterns that we've seen yet. Ammonium is a polyatomic ion, but it's a polyatomic cation. It's NH4 with a +1. So if you look on your polyatomic ion list, the second one on there is ammonium. And then cyanide is a polyatomic ion that's going to be Cn-. And you'd have those you just kind of have to know because they're different from the rest. All right. Cyanide and hydroxide are the only 2 polyatomic ions that end in IDE. Ammonium is the only one that ends in IUM. So just be kind of aware of that when you're doing these. This sheet is really just for practice. So again, I want to make sure that you're practicing this and recognizing that this is strictly ionic compounds on this one. Ionic compounds contain both a metal and a nonmetal, or a positive ion and a negative ion. So in this case, it contains two polyatomic ions, but one is positive and one is negative. So we have to recognize what's happening there. So it's going to have 4 different elements in it when we do that one. All right, so I'll just kind of show you this one. So 25 should ended up being, let me make sure that I got sulfate right. Yeah. It'd be NH4 2. Be written like that. All right. So again, that's ionic compounds. Today we're going to the stuff that we're going to do today is covalent. Covalent is a lot easier than ionic. So for covalent compounds, we're going to be doing the same thing. We're going to be going from name to formula, a formula to name. We have to be able to go both ways. But covalent compounds uses the numbers of the subscripts that we have in the equations actually get a prefix in the name. So we'll be using the Greek prefixes. And so mono, di, tri, tetra, penta, hexa, hepta, octa, nona. All right. All right. So going through here, the first thing that I want to introduce for when we're dealing with covalent compounds, which we're also going to call molecular compounds. When we're writing the names of these, we're going to include these Greek prefixes from 1 to 10. None of the ones that I'll give you will be greater than 10, a subscript of 10 ever. So the prefixes that we use is mono is 1, di is 2, tri is 3, tetra is 4, penta is 5. So if you think about your polygonal shapes and all of that, the names of those, that follows that. Hexa is 6, hepta is 7, octa is 8, nona is 9, and deca is 10. All right. That's going to be very important in the naming. So the nice thing about covalent compounds, the name tells you exactly what's there. All right, versus ionic. Ionic is relying on charge comparison, so that's how we determine the formula. Covalent, the name tells us exactly what's there. So there's a lot less to this one than there was to the other. So I'll give you all a minute to make sure. The 2 things that I need you to have from this is just knowing that covalent compounds are also called molecular, and then know our Greek numeric prefixes. Where'd it go? So because I'm introducing a new type of compound, one of the key things is that we're going to have to be able to distinguish when we look at a compound or look at a name, be able to distinguish, is it ionic or is it covalent now? Because there's two different sets of rules for naming these. So you have to be able to look at the formula and know which is which. So anybody else need more time before I switch slides? All right. So I want us to recall when we're dealing with ionic compounds, I'm going to look for the presence of a metal in the compound. That's going to be the easiest way to identify that something is ionic. All right. When we are dealing with covalent, also called molecular, when we're dealing with covalent compounds contain only nonmetals. So you will only see elements in a covalent compound. The only elements in there are going to be in this region. Even though it's a very small area, there's a lot of compounds that contain that. All right. So again, our goal today is to be able to name and or write a covalent compound. Name it or write the formula. All right, so here are the rules for naming covalent compounds. All right, name the first element, name the second element. On the second element, we're going to change the ending to IDE, so we only ever do it for the second one. And then we're going to use the prefixes on those two names to identify what the subscript for each one is. So you've already done this and you already recognize this because what do we call CO2? We call it carbon oxide, and because of the two, we say di. Now, notice I didn't write monocarbon dioxide. When it's the first element, we don't have to write the mono, all right? But the second element, we always have to have a prefix for the number. So even if it was just one, so for example, CO is carbon monoxide. All right, so we always have to have the prefix on the second one. All right. All right, so I'm going to revisit my Greek prefix number list again, just real briefly, because I'm going to make sure I make this distinction. So we'll use prefixes on the names when we do this. The mono we don't put on the very first atom because just by nature of saying the name, we know we have at least one. But when it's the second atom, we need to tell how many is in there, so we have to write it there. Everything else, if it's any more than one on it, you're going to have to show it. All right. Does anybody need more time on this slide? All right. So going back to this. So remember these prefixes, mono is 1, di is 2, tri is 3, tetra is 4, penta is 5, hexa is 6, hepta is 7, octa is 8, nona is 9, and deca is 10. The mono, again, we only include it if it's the second atom that has 1. All right, we don't ever put mono on the first name. So if the first element only has one, then we don't use mono. We just say what the element is. So let's try to come up with a name for this one. Go ahead, write it on your paper. Write down the name that you think, and then we will we'll go over it. All right. So what do y'all think? Sulfur trioxide. All right. So like I said, covalent's going to end up being a lot easier than ionic was. That's the reason why I do ionic first, because I want you to get the more challenging one so you have more time to think about it. Covalent is a lot easier. Now, how do you know this one? How would we look at this and just automatically know that it's covalent? No metals. Everything is to the right side of the period of that metalloid line. All right. Now, if I saw this name and not the formula, what about the name would tell me that it's covalent and not ionic? The presence of that tells me it's covalent. If I see that mon, tri, deca, whatever in the name, I pretty much know it's covalent at that point. All right. This is a formula, not a statement. Go ahead, write down what you think this one is, and then we'll go on. All right, anybody want to venture a guess what they think this one is? Nitrogen monoxide. All right. Now, notice that I didn't write monoxide. Since oxygen begins with the vowel, I just merged them together. And so on these, you're going to have to play with that placement of the vowel. Like with penta, I wouldn't say, if this was NO5, I wouldn't say nitrogen pentaoxide. I would say nitrogen pent oxide. I would drop the vowel off the end. But if it's a consonant on the first letter of the element, sometimes I'll keep the vowel. You really just kind of have to play with it and see which one sounds right in your head. All right, go ahead, do this one. All right. So anybody care to venture a guess? Phosphorus hexachloride. And that one's probably just because it's unfamiliar to you. All right. Now, flipping it the other way, going from the name to the formula. All I really do is I look at the name, I look at the prefixes. So dinitrogen, what is my symbol for nitrogen? My symbol for nitrogen is an N. The di tells me it's going to be N2. Oxide is O. And pent tells me it's 5. So go ahead, try the rest of these, and I'll write the answers in a minute.
I wish I knew how to do that. Yeah. Oh my god, Molly's making me so mad. They're so cute. I remember like one note title was like the 1970s and 80s.